Somewhere out there, past the moon, past the asteroid belt, past the quiet dark between worlds, there are two planets we keep arguing about. One is red and cold and dusty. The other glows like a lantern in the evening sky. And for decades now, we've been so focused on the red one that we've almost forgotten to look at the bright one. Tonight, we're going to slow down and look, really look, because when you do, something surprising starts to happen. The case for Venus, not Mars, as our first home beyond Earth starts to feel not just possible, but obvious. And it starts at the beginning. Before you can build anything on another world, you have to get there. And the way we measure that journey in spaceflight isn't in miles or kilometers. It's in something called delta V. Think of delta V as the total amount of push your rocket needs to change its speed, to leave Earth's gravity, cruise through space, slow down, and arrive somewhere safely. The higher the delta V, the more fuel you need. The more fuel you need, the heavier and more expensive your mission becomes. So when we compare Mars and Venus, the first question isn't which one is closer on a map. It's which one costs less energy to reach. And here is where the story gets interesting. Most people assume Mars is the natural next step because it feels like the right direction, outward, away from the sun, toward the frontier. But when you run the actual numbers, Venus wins on energy. A mission using what's called a Hohmann transfer orbit, the most fuel-efficient path between two planets, requires noticeably less delta V to reach Venus than to reach Mars on certain mission profiles. Now, that comparison gets more complicated when you factor in what a Venus mission actually looks like. There's no surface to land on. The colony floats, which means any mission has to include aerobraking, aerocapture, and aerostat deployment, steps that add their own energy costs back in. So the raw delta V number is not the whole story. What we can say honestly is that the basic trajectory to Venus starts from a more efficient baseline, and that matters when you're thinking about hundreds of missions over decades, even if the advantage on any single mission is harder to pin down precisely. Now add another layer to this. Planets don't sit still. They orbit the sun at different speeds, which means the window of time when a mission is actually practical, when Earth and your target planet are aligned correctly, opens and closes on a schedule. For Mars, that window opens roughly every 26 months. You miss it, you wait over 2 years. For Venus, the window opens every 19 months. That's a 7-month difference. For a colony that needs regular resupply of medicine, spare parts, food, and people, 7 months is not a small gap. It could mean the difference between a thriving settlement and a desperate one running low on essentials. Think of it this way. Imagine you are running a remote research station in Antarctica. You can get resupplied either every 19 months or every 26 months. Which one feels safer? Which one feels more like a place you could actually live long term? The answer shapes everything. Supply chains are not just logistics. They are lifelines. And a colony that gets resupplied more often is a colony that survives mistakes, adapts faster, and grows more confidently. There's also the question of the return trip. If something goes wrong, a medical emergency, a systems failure, a human decision to simply come home, Venus offers a faster, more frequent path back to Earth. On Mars, an emergency return is a 26-month wait at worst. On Venus, that window comes around sooner. That psychological reality matters both for the settlers who go and for the families they leave behind. Now, none of this means the journey to Venus is easy. It isn't. Any interplanetary mission is a massive engineering challenge. But when we're deciding where to invest the first $1 trillion of colonization infrastructure, where to build the first roads and the first hospitals and the first schools beyond Earth, the energy cost and the resupply frequency are not minor footnotes. They are the foundation everything else is built on. And on that foundation, Venus already has an edge. So before we've even talked about what it's like to actually live there, the air, the temperature, the pressure, the remarkable and strange physics of a floating city in the clouds, Venus has already taken the first point. It is, in the most literal and measurable sense, more reachable than the planet we spent the last 50 years dreaming about. That sets us up for the part of this story that most people have never heard. So let's talk about what it's actually like to live there. When most people picture a Mars colony, they picture something like a base camp, a cluster of pressurized modules half buried in red dirt, small windows, thick walls, airlocks you cycle through before stepping outside in a suit that keeps you alive in an atmosphere so thin it barely registers. The sky outside is a pale, dusty pink. The temperature swings from manageable cold to brutal cold. depending on the season and the time of day. And beneath your feet, the ground is laced with perchlorates, toxic chemical compounds in the Martian soil that make growing food directly in it somewhere between difficult and dangerous. You are in every meaningful sense living in a bunker. Now picture Venus, not the surface. The surface of Venus is genuinely hostile in ways that make Mars look inviting. Down there, the temperature hovers around 460 degrees Celsius. The atmospheric pressure is 90 times what we feel on Earth. Lead melts. Soviet probes sent to the surface in the 70s and 80s lasted between 23 minutes and 2 hours before the planet simply crushed and cooked them. Nobody is suggesting we build a home down there. But here's the thing. Nobody has to. Because roughly 50 to 55 kilometers above that scorched surface, something remarkable happens. The atmosphere of Venus reaches a zone where the pressure settles to almost exactly 1 bar. The same pressure you feel right now, sitting or lying wherever you are. The temperature across that band ranges quite a bit depending on exact altitude and latitude, from near freezing at the upper edge to as warm as 75 degrees Celsius lower down. Within certain narrow slices of that zone, you find temperatures closer to a mild spring day. It is not uniformly comfortable across the whole 50 to 55 kilometer range, and the engineering of a habitat would need to account for that variation carefully. And the gravity pulling you toward the planet below is about 91% of what you feel on Earth. Your body would barely notice the difference. On pressure and temperature, this zone is among the most Earth-like environments in the solar system outside of Earth itself. More Earth-like than the surface of Mars on those two measures. But it is worth being precise about that claim, because Venus is not Earth-like in every way. The day length on Venus is 243 Earth days, longer than its own year. The sun, when it does appear through the clouds, moves across the sky in a way that has nothing to do with the rhythm human bodies evolved inside. Circadian biology, sleep cycles, the psychological regularity of day and night, all of that would require artificial management inside the habitat. Lights on a timer, a manufactured sense of morning and evening. It is solvable the same way it is solved on a submarine or a polar research station. But it is not a small thing to set aside. And there is an engineer named Geoffrey Landis, working at NASA, who looked at that zone and asked a simple question. What if we just lived there? His concept, developed alongside other researchers and eventually formalized under the name HAVOC, which stands for High Altitude Venus Operational Concept, describes a colony that never touches the Venusian surface at all. Instead, it floats. Giant aerostats, which are essentially very large and very carefully designed airships, drifting in that cloud layer 50 kilometers up. And here is the part that makes this feel almost like a trick of physics. The air inside those habitats, ordinary breathable air, the oxygen and nitrogen mix we've always lived in, is actually less dense than the carbon dioxide atmosphere of Venus surrounding it, which means breathable air acts as a lifting gas on Venus the same way helium lifts a balloon here on Earth. The habitat breathes, and in breathing, it floats. But it is worth pausing on what that actually requires. The lifting force of breathable air in a carbon dioxide atmosphere is real, but it is not strong to lift meaningful mass, the kind of mass a habitat for dozens or hundreds of people would involve. The enveloped structure itself would need to be enormous. We are talking about structures potentially kilometers across. That is not a reason to dismiss the idea. It is a reason to take the engineering seriously. And to be honest that this is not a small balloon. It is one of the largest structures humanity would ever attempt to build, and it would need to be built and deployed above a planet we have barely visited. You are not fighting the environment to stay alive. You are using it. The air that keeps you breathing is the same air that keeps you aloft. The structure doesn't need to hold pressure inward against a vacuum the way a Mars habitat does. It simply needs to keep the outside atmosphere out. That is a fundamentally different and, in many ways, simpler engineering problem. Compare that to Mars. On Mars, every habitat is a pressure vessel under constant stress. The thin atmosphere outside is trying to let the pressure inside escape. Radiation from the sun streams through without much protection. Settlers would likely spend much of their time underground, trading the psychological weight of isolation for the physical protection of rock and regolith above their heads. There is one place where this comparison tilts back toward Mars, and it deserves to be said plainly. On Mars, if something goes seriously wrong, a breach, a seal failure, a structural problem, there is ground beneath you. You are not falling anywhere. A Mars surface habitat can fail in degrees. On Venus, at 50 kilometers up, a catastrophic failure of the aerostat envelope is a different kind of event entirely. Below you is an atmosphere that reaches 460 degrees and 90 times Earth's pressure. There is no emergency walk outside. There is no EVA to patch something from the exterior in a crisis. The failure mode at the extreme end is total. That is not a reason to stop thinking about Venus, but it is a reason the redundancy and structural integrity of any aerostat design would need to be held to a standard we have never engineered for before. On Venus, at 50 kilometers up, you have the atmospheric equivalent of a warm spring afternoon. You have pressure. You have gravity close enough to Earth's that your bones and muscles would stay strong across a lifetime. You have a structure that, in principle, could be made large enough to walk around in, to grow food in, to raise children in. It is not a bunker. It is a city in the clouds. Now, a floating city in the clouds is a beautiful idea, but beauty doesn't keep people alive. What keeps people alive is air, water, and food. And the moment you're 50 million miles from Earth, the question of where those things come from stops being philosophical. It becomes the most urgent engineering problem you have. So let's talk about resources, and let's be honest about both planets. On Mars, the story of resources is a story of searching. Water exists there, we know that. There is ice at the poles, and there is evidence of water frozen beneath the surface in various regions. But accessing it means landing equipment, drilling or excavating, melting and purifying, and then moving that water to wherever the colony needs it. The Martian atmosphere is about 96% carbon dioxide, which sounds useful. You can, in theory, extract oxygen from it. NASA actually tested a small version of this with an experiment called MOXIE on the Perseverance rover, and it worked. That's genuinely exciting and worth taking seriously. MOXIE demonstrated the chemistry is viable in actual Martian conditions. What MOXIE was not is a production system. It was a 17-kilogram proof of concept, roughly the size of a car battery, designed to show the principle could function, not to supply a colony. Scaling from a successful lab demonstration to an oxygen supply chain that keeps hundreds of people alive is a real engineering path, but it is a long one. And throughout that path, you're still pulling from an atmosphere so thin it barely registers. The raw material is sparse, and the energy costs of extracting from near vacuum at scale remain a serious challenge that MOXIE's success does not dissolve. The soil presents its own problem. Martian regolith contains perchlorates, toxic salts that have to be removed before anything can be safely grown in it. That is not an impossible problem, but it is an extra step. An extra process, an extra point of failure in a system where failure has very serious consequences. Mars forces you to work for every molecule. Venus takes a different approach entirely, or rather, Venus offers a different kind of abundance. The atmosphere of Venus, the same thick envelope of gas that makes the surface uninhabitable, is roughly 96.5% carbon dioxide and about 3.5% nitrogen, carbon and oxygen and nitrogen. The three elements you need most to build breathable air and to grow food. They are not buried underground. They are not locked in frozen polar deposits. They are everywhere, in enormous quantities surrounding the colony on all sides at all times. Water is trickier, but it is there. The cloud layers of Venus contain sulfuric acid droplets, and within those droplets there is water vapor. Extracting it requires processing. You have to neutralize the acid and collect the water, but the raw material is constant and passive. You don't send a rover out to find it. You filter it from the air your habitat is already floating through. There is one resupply problem that deserves to be named directly because we have praised Venus's 19-month window without addressing it. Getting cargo from Earth orbit to a habitat floating at 50 kilometers is not the same problem as landing a supply ship on a solid surface. You cannot land. Dropping payloads through the sulfuric acid cloud layers requires the cargo to survive that transit and then rendezvous and dock with a structure that is drifting in a moving atmosphere, not anchored to the ground. This is a genuinely unsolved engineering challenge. Concepts exist involving aeroshell-protected drop packages, tethered docking systems, and atmospheric entry profiles designed to match the habitat's altitude and drift. None of them have been demonstrated. The resupply frequency advantage Venus holds over Mars is real in terms of orbital mechanics. Whether the delivery problem can be solved reliably enough to make that frequency meaningful in practice is one of the most important open questions in the entire Venus colonization concept, and it belongs on the table alongside the advantages. Think about the distinction that remains even with that challenge acknowledged. On Mars, your colony is like a desert outpost that has to send expeditions out to find and haul back every drop of water and every breath of oxygen. On Venus, your colony is more like a ship at sea. The ocean is right there. You just have to know how to draw from it. There is also the question of energy. Venus is closer to the Sun than either Earth or Mars. At the altitude where a cloud city would float, Venus receives more solar flux at the top of its atmosphere than Mars does. But the cloud layers are highly reflective. Venus bounces back roughly 75% of incoming sunlight. And how much usable irradiance actually reaches a solar panel at 50 kilometers is genuinely debated. Some models suggest it falls below what a panel would receive on the Martian surface. The honest answer is that the solar energy comparison between the two is unclear, and any Venus colony would need to treat power generation as an open engineering question rather than an assumed advantage. What Venus does avoid is the global dust storms that can coat Martian solar panels and cut power for weeks at a time. That operational reliability matters, even if the raw numbers are unsettled. So when you look at the full picture of life support, air, water, energy, the Venusian atmosphere stops looking like a hostile environment and starts looking like a supply depot. A vast, passive, continuously available source of almost everything a colony needs to sustain itself. The engineering challenge is not finding the resources. The engineering challenge is building the filters and processes to access resources that are already right there, and solving the delivery problem of getting additional supplies down from orbit. That is a very different problem to solve, and in engineering terms, it is a much more forgiving one. A colony that filters its air from the sky around it is a colony that can recover from setbacks. A colony that has to mine every essential molecule from the ground beneath it is one that lives closer to the edge. There is something we don't talk about enough when we imagine life on another planet. Not the rockets, not the habitats, not the food. Something quieter. Something that only becomes real when you are the one who is far away. It is the silence between a question and an answer. When you send a radio signal from another planet, it travels at the speed of light. Nothing in the universe moves faster. And yet, even at that speed, the distances involved in interplanetary travel mean that your message takes time to arrive. Real, measurable, sometimes agonizing time. From Earth to Mars, depending on where both planets are in their orbits, a signal takes somewhere between 3 and 22 minutes to arrive. From Earth to Venus, that range runs from about 2 minutes to 14. Those numbers might look similar at first glance, but in practice they describe very different realities. Think about what a 14-minute one-way delay actually means. If something goes wrong in a Venus cloud city, a pressure seal failing, a medical emergency, a navigation system glitching, and the crew sends a message asking for help, the earliest Earth can respond is 14 minutes later. In a real emergency, that is a long time, but it is a manageable time. Crew protocols can be designed around it. Mission controllers on Earth, who have access to far more data and expertise than any small crew can carry, are still meaningfully in the loop. Now stretch that delay to 22 minutes each way on a bad Mars day. Your crew sends a distress call. 44 minutes pass before they even know Earth received it. That is not a communication gap. That is a near total separation. The crew is, for all practical purposes, on their own. This matters in ways that go beyond emergencies. Think about the software update that patches a flaw in the life support system, the medical diagnosis that requires a specialist back on Earth to review scans and offer guidance, the navigation correction that needs to happen before a resupply vessel docks. All of these become slower, more dangerous, and more uncertain with every minute of lag added to the line. One thing this comparison has to acknowledge plainly: Venus, like Mars, passes through superior conjunction, the point in its orbit where it moves behind the Sun from Earth's perspective. During that window, which lasts roughly 2 weeks for Venus, direct radio communication is blocked entirely. For that brief period, a Venus colony would be in the same complete communication silence that Mars settlers face during their own conjunction. The advantage Venus holds in average signal delay and minimum lag is real across the bulk of each orbital cycle, but it is not continuous, and mission planning would have to account for those blackout windows the same way any interplanetary mission does. And then there is the human dimension, the part that doesn't show up in technical papers but that anyone who has ever spent time far from home understands immediately. The feeling of distance, the weight of it. On Venus, at the closest approach, a settler could exchange messages with someone on Earth in under 5 minutes round trip. A conversation, stretched and slow but still a conversation. A parent asking about a grandchild. A doctor checking in on a patient. A friend just saying hello. These things sound small. They are not small. For people living in a floating habitat above an alien world, These threads back to Earth are part of what makes the experiment survivable, not just physically, but mentally. Mars severs those threads more completely. The isolation is deeper, and we have very little understanding of what sustained, profound isolation does to people over years and decades. It is one of the quieter unknowns in the Mars colonization plan, and it is one that gets far less attention than rockets and radiation. Venus, by virtue of its orbit, stays closer to Earth in the only currency that ultimately matters between peoples separated by space: the speed of thought, the time it takes for one human mind to reach another. And on that measure, Venus is, again, the nearer world. We've talked about getting there. We've talked about floating in the clouds, filtering the air, staying in touch with home. But all of that is short-term thinking. And the question that matters most, the one that separates a temporary outpost from a true second home for our species, is a longer one. Can people actually live there? Not for a mission, not for a few years, but for generations. This is where the comparison between Venus and Mars becomes the most stark, and it comes down to something so basic, so fundamental to what we are as biological creatures, that it almost feels too simple to be the deciding factor. It is gravity. Mars has 38% of Earth's gravity. If you stood on the surface of Mars, you would weigh a little more than a third of what you weigh right now. That sounds freeing at first, almost pleasant. But your body was not built for that world. Your bones, your cardiovascular system, your muscles, the fluid pressure in your eyes, all of it was shaped over millions of years to function under one full gravity. We already know from decades of research on astronauts aboard the International Space Station that extended time in low gravity causes measurable bone loss, muscle atrophy, vision problems, and cardiovascular changes. Some of those effects reverse when people return to Earth, but on Mars there is no returning to Earth for most settlers. That is the point. Mars is home now, and we simply do not know what 38% gravity does to a human body over a lifetime. We don't know what it does to a child growing up in it. We don't know whether babies can be carried to term safely, whether developing bones and brains form correctly, whether the second generation of Martian settlers would even be healthy enough to carry on. These are not small uncertainties. They are foundational ones. The entire project of a self-sustaining colony rests on the ability of people to reproduce and raise healthy children, and on Mars, that ability is in serious question. Venus at 50 kilometers altitude pulls you downward with 91% of Earth's gravity. The long-term health effects of 0.91 gravity on the human body are very likely minimal. To be precise about what we do and don't know, we have good data on zero gravity from decades of ISS research, and we have a lifetime of data on one full gravity from living on Earth. The range between those 2 points, including 0.91, has not been systematically studied. The expectation, grounded in the pattern of how gravity-related health effects scale, is that the gap from 1G to 0.91G would be far smaller than the gap from 1G to the 0G or low G environments we know cause measurable harm, but expected to be minimal and proven to be negligible are not the same claim, and it would be imprecise to treat them as equivalent. Children born in a Venus cloud city would grow up in a gravitational environment close enough to Earth's that their bones, their hearts, their eyes, their development would follow something close to the path evolution prepared them for. That is not a minor advantage. That is the difference between a colony that might sustain itself and a colony that almost certainly can. Then there is the longer view still, the question of what these planets could eventually become. Terraforming, the idea of reshaping a planet's environment to make it more Earth-like, is a multi-generational dream, but it is one worth holding. Mars would require building an atmosphere essentially from nothing. The planet lost most of its magnetic field long ago, and without that field, any atmosphere we tried to build would slowly be stripped away by the solar wind. Venus, it should be said, also lacks a meaningful magnetic field. Solar wind strips ions from its upper atmosphere too. Neither planet offers the kind of magnetic protection Earth does. A cloud city on Venus would still need to think carefully about radiation exposure, particularly during solar events, even though the thick atmosphere below provides some shielding by mass. The proposals for fixing this involve planetary-scale engineering on timescales of thousands of years, and they start from a very thin foundation. Venus is different. Venus already has a thick atmosphere, already has near-Earth gravity, already has a day that, while extremely long, could in theory be managed. The challenge on Venus is not building something from scratch. It is reshaping something that already exists. Carl Sagan, in one of his earliest scientific papers back in 1961, imagined introducing microbes into the Venusian atmosphere to begin breaking down the carbon dioxide. The ideas have grown more sophisticated since then. Solar shades to cool the planet, chemical processes to bind the carbon. The details are complex and the timescales still immense, but the starting point is better. A planet that already has the right gravity. A planet that already has the right size. A planet that is, in the language of planetary science, Earth's twin, older and hotter and stranger, but built to the same basic blueprint. The long game on Venus begins from a position of natural similarity. The long game on Mars begins from a deficit that may never be fully closed. And when we are talking about the future of our species, where we begin matters enormously. So we've moved through 5 separate ideas: energy costs and launch windows, floating habitats in temperate cloud layers, atmospheric resources filtered like water from a river, communication delays measured in minutes rather than hours, and the deep generational question of gravity and what it means for the human body across a lifetime. Each one, on its own, already shifts the comparison. But here is what I want you to sit with for a moment before we go any further. These are not 5 separate arguments. They are one argument, a single connected system where each part makes the others stronger. And once you see it that way, the picture becomes much clearer. Start with the first piece. The energy cost of getting to Venus is lower, and the launch windows open more often. That matters on its own. But it matters even more when you remember what the second piece told us, that a Venus colony doesn't sit on a surface at all. It floats, and a floating habitat, by its nature, is more modular, more expandable, more repairable than a buried bunker on Mars. What does more frequent resupply make possible? It makes maintaining and growing that floating structure far more practical. Spare parts arrive sooner. New modules can be added on a faster schedule. The colony can grow with confidence rather than rationing every component against the long wait for the next cargo window. Now bring in the third piece. The atmosphere that holds the colony aloft is the same atmosphere the colony draws its air and water from. The habitat doesn't just float in its resource base, it is surrounded by it, and because resupply windows come more often, the colony is never more than 19 months away from a top-up of anything the atmosphere can't provide. The filtering systems that pull breathable air and water vapor from the clouds around the habitat are not backup systems, they are the primary ones. The resupply chain from Earth fills in the gaps. That is a deeply stable arrangement, provided the unsolved delivery problem, getting cargo down through the acid clouds to a drifting habitat, is eventually resolved. That caveat matters, and it is real. Then layer in the fourth piece. Shorter communication lag means that the engineers and doctors and mission controllers on Earth who designed those filtering systems, those structural connections, those habitat modules, can stay meaningfully involved in running them. They are not cut off by distance. They are partners across a manageable delay. When a filter degrades faster than expected, or a new resource need emerges, the people on Earth with the expertise and the computing power to solve it are still, functionally, in the room. The colony is not alone, and all of that, the reachability, the floating structure, the passive resource access, the connection to home, serves the fifth piece, the long-term goal, raising people who are healthy. Building a community that can sustain itself not just for 5 years or 10, but for generations. That goal requires every other piece to be working. It requires resupply. It requires a livable environment. It requires resources that don't run dry. It requires people who don't feel completely severed from the world they came from. Venus, at 50 kilometers up, offers a version of all of those things working together. Mars, by contrast, is a system of deficits compounding each other. Harder to reach means resupply is rarer, which makes every resource shortage more dangerous, which deepens the isolation, which puts more pressure on a colony already dealing with gravity that may harm the very children it is trying to raise. Each problem makes the others heavier. That is the real difference between these two worlds. Venus presents a set of challenges that ease each other. Mars presents a set of challenges that amplify each other. And when you are building something meant to last, that distinction is everything. There is something we have been quietly stepping around. You have probably noticed it, and it would not be right to keep moving without addressing it directly, because any honest look at Venus has to reckon with it. The clouds are made of sulfuric acid, not a trace of it, not an occasional wisp. The same cloud layer we have been describing as temperate and pressurized and almost comfortable is also a persistent mist of sulfuric acid droplets. Fine ones, small enough that you would barely see them in the air around you, but they are there. And they are corrosive, and any structure we place in that environment will be in continuous contact with them. So let's sit with that honestly for a moment, without dismissing it, and without exaggerating it either. The first thing worth knowing is what that acid actually looks like at 50 kilometers up. It is not the fuming, boiling liquid you might picture from a chemistry classroom. At that altitude, the temperature and pressure conditions produce a fine mist, droplets just a few microns across, dispersed through the atmosphere like a very thin fog. The distinction matters because the engineering challenge of a fine acid mist is fundamentally different from the challenge of liquid immersion. You are not submerged. You are drifting through something closer to a light, persistent drizzle that happens to be chemically aggressive. And here is the thing about corrosive environments. We have been building structures inside them for a long time. Industrial chemical plants process acids far more concentrated than what Venus's clouds contain. Offshore platforms sit in salt water for decades, and salt water is corrosive in its own quiet, persistent way. Pipes and vessels designed to handle hydrofluoric acid, hydrochloric acid, and concentrated sulfuric acid are built and operated routinely on Earth. The materials science involved is not experimental, it is established. Fluoropolymer coatings, the same family of materials that includes the non-stick surface on a frying pan, are highly resistant to sulfuric acid. Certain nickel alloys hold up well under prolonged exposure. Titanium is largely unaffected. Passive condensation systems can continuously clear acid droplets from surfaces before they accumulate enough to cause meaningful damage. None of that is trivial. It requires care, redundancy, and ongoing maintenance. It is real engineering work, and we should treat it as such, but it is engineering. It belongs to the category of problems we know how to think about, test, iterate on, and solve. The acid is a known obstacle. We can see it clearly. We can measure it. We can design around it. Now hold that against some of the open questions on the other side of this comparison. We do not have a proven answer for what 38% gravity does to a human body across 20 years. We do not have a working method for protecting a Martian surface atmosphere from being slowly stripped away by solar wind. We do not know whether children can be born and develop healthily in Martian gravity. These are not engineering problems in the ordinary sense. They are open questions in biology and planetary physics, and some of them may not have good answers at all, no matter how clever the engineering gets. There is a useful way to hold this distinction. Some problems yield to better materials, some yield to better chemistry, and some are written into physical laws in ways that no amount of ingenuity can fully rewrite. The acid sits in the first category, gravity sits in the last. That does not make Venus simple, it makes Venus solvable. So if the physics leans this consistently toward Venus, you might find yourself asking a quiet question. Why aren't we already planning cloud cities? Why did the rovers keep rolling across red dust? Why does every major announcement about humanity's future beyond Earth point in the same familiar direction? The answer isn't physics. It never really was. It's narrative. Mars has a story, and it is a very good one. It's a desert frontier, vast and silent, and, in a certain light, almost beautiful. There is something in it that echoes the oldest human instincts about exploration. The open horizon, the unknown terrain, the sense that if you just walked far enough, you might find something no one has ever seen. You can look at the photographs sent back by the Perseverance rover and feel the ground under your feet. Even from 100 million miles away, Mars looks like a place you could go. Harsh, yes. Inhospitable, certainly. But solid, real in the way that deserts and mountains are real. Venus doesn't give you that. Venus gives you clouds. And clouds, however scientifically remarkable, are harder to inhabit in your imagination. You can't plant a flag in them. You can't picture yourself standing on them and staring at a horizon. The image of a floating city 50 kilometers above a crushing, acid-soaked surface requires more from a listener than most people are asked to give in a single conversation. And so the story never quite takes hold the way the Mars story has. Then there is the matter of who has been doing the loudest talking. Elon Musk has been explicit and consistent for many years now. Mars is the destination. The entire long-term architecture of SpaceX, the Starship vehicle, the refueling concepts, the ambition of a self-sustaining city on another world is oriented toward Mars with a clarity of purpose that has quietly reshaped the public conversation around space. When a company with that kind of momentum names its target, that target becomes the target. Funding follows vision, and vision in this case has been given an enormous platform. Robert Zubrin, the aerospace engineer who founded the Mars Society, spent decades making the case for Mars with similar intensity. His Mars Direct proposal laid out a lean, achievable path to the red planet that captured the imagination of a generation of engineers. It was a compelling argument, made compellingly, and it worked. It shifted the conversation in ways that still echo today. Venus hasn't had that champion, not at that scale. Geoffrey Landis made the scientific case carefully, and the HAVOC concept is genuinely elegant. ESA's Envision mission and the DAVN C+ probe represent real institutional interest. Sarah Seeger at MIT has done important atmospheric science work that touches on Venus among her broader contributions to planetary research. The scientific community has not ignored Venus, but the colonization conversation, the large, public, emotionally resonant version of it, has not yet found its voice there. And so the funding follows the story. Mars gets rovers, sample return missions and international partnerships. Venus gets probes. Important ones. Careful ones. But not the kind of flagship momentum that signals a civilization making a deliberate choice. What is worth sitting with quietly is the gap between what is popular and what is practical. History has a long list of paths chosen not because they were the wisest ones, but because someone told a compelling story about them first. The clouds of Venus are patient. The physics isn't going anywhere. Only the conversation needs to shift. There is one place where Mars wins this comparison cleanly, and it is worth saying so directly, because the whole point of looking at this carefully is to see it honestly, not to arrive at a conclusion we decided on before we started. Mars is closer to being reachable right now. The technology path to a crewed Mars mission is, in the language of aerospace engineers, relatively well defined. We know how to build rockets large enough to carry people there. We understand the basic shape of a surface habitat. We have landed rovers, orbiters, and probes on Mars with increasing precision and reliability. NASA's current planning puts a crewed Mars landing somewhere in the 2030s. A permanent or semi-permanent base, depending on how the program develops, could exist by the 2040s. That timeline is ambitious, and it will almost certainly slick the way ambitious timelines always do. But the direction is clear. The path from here to there is, at least in its broad outline, something engineers can trace. Venus is not there yet, not for crewed missions. The specific challenges of operating in the Venetian cloud layer require more upfront development work than simply landing a pressurized module on solid ground. Before we send human beings to float above Venus, we need robotic missions specifically designed to test the relevant systems in the actual environment, not in simulations. Not in Earth-based analog conditions, in the clouds themselves for real, over real timescales. We need to understand how candidate materials hold up against the acid mist across months and years of continuous exposure. We need to demonstrate that an aerostat can be deployed reliably at altitude, stabilized, and maintained without a crew there to fix problems by hand. We need to learn things we currently do not know. And learning them takes time and money and sustained attention from the people and institutions capable of doing it. A realistic timeline for a crewed Venus atmospheric mission probably sits in the 2050s at the earliest, possibly the 2060s, depending on how seriously the next decade of robotic exploration is funded. That is a meaningful gap, a full generation of engineering work separating the two destinations. So the honest framing is this: Mars is the nearer step. Venus is the better destination, and both of those things can be true at the same time without one cancelling the other out. Think of it the way you might think about a long journey with two possible stops along the way. The first stop is closer and easier to reach with what you already have. The second stop is farther, requires more preparation, but is the place you actually want to end up. Choosing the first stop first is not a mistake. It only becomes a mistake if you forget that the second stop exists, or if you spend so much building at the first one that you never leave. The question worth sitting with is whether we are making that choice consciously, eyes open, with Venus on the horizon, or whether we are simply defaulting to Mars because it is the option the current moment can most easily imagine. That is not a technical question. It is a strategic one, and the answer we give over the next few decades of planning and funding will shape, in ways that are difficult to overstate, where our species actually ends up. So let's bring it together. 5 areas, 2 planets, and an honest accounting of what the weight of each argument actually tells us. On the energy cost of getting there, the delta V, the launch window frequency, the basic logistical rhythm of keeping a colony alive across decades, Venus holds the advantage. Lower energy requirements per mission, windows that open more often, a cumulative efficiency that compounds across hundreds of resupply runs over many years. Venus takes that one. On habitat design, the livability of the environment, the pressure, the temperature, the gravity, the structural logic of the colony itself, Venus holds the advantage again. 91% Earth gravity, 1 bar of pressure, a mild stable temperature band within the right altitude slice, a floating structure that uses breathable air as its own lifting gas. The cloud layer at 50 kilometers is genuinely hospitable in a way that the Martian surface simply is not. Venus takes that one too. On resources. The availability of air, water, nitrogen, carbon, and solar energy without sending expeditions across a hostile terrain to find them. Venus holds the advantage, with the important caveat that the delivery problem of getting supplies from orbit down to a floating habitat remains unsolved. The atmosphere surrounding the colony is its supply chain. Everything drifts past continuously. Mars requires active searching and mining across an unforgiving surface where even the soil itself needs to be treated before it can grow anything. Venus again, with that asterisk acknowledged. On communication, the signal delay, the practical ability to get guidance from Earth in a crisis, the psychological thread that keeps a small group of people from feeling entirely alone in an alien environment. Venus holds the advantage. Shorter average lag, across the full range of orbital positions, every single year, with the same conjunction blackouts that Mars also faces. Venus again. On long-term human viability, gravity's effect on the body across a lifetime, the possibility of raising healthy children, the quiet but foundational question of whether a civilization can actually take root and grow. Venus holds its most important advantage of all, near-Earth gravity versus a gravitational environment we have never tested across a human generation and cannot currently change. Venus again. That leaves one criterion: current technology readiness, the nearness of the engineering path from today to first human presence. And here, Mars wins. The gap is measured in decades, not centuries. But it is real, across the 5 areas we looked at: energy cost, habitat livability, resource access, communication lag, and long-term human health. Venus holds meaningful advantages. Mars wins clearly on current technology readiness, and that is not a small thing. It is worth being honest that these 5 criteria were not handed down from some neutral authority. They are the ones this particular comparison focused on. You could build a different list: solid ground to stand on, existing rover infrastructure, lower catastrophic failure risk, a day length close to Earth's, no unsolved cargo delivery problem. And Mars would look much stronger. Both framings are real. Both sets of criteria matter. What the weight of this comparison suggests is not that Venus is obviously correct and Mars is obviously wrong. It is that Venus deserves a seat at the table it has not been given, that the conversation has not been as balanced as the physics warrants, and that some of the advantages we have taken for granted on the Mars side look less solid when you examine them carefully, just as some of the challenges on the Venus side look more manageable when you stop treating them as deal breakers and start treating them as engineering problems. Perhaps that is the most honest thing we can say about both of them. The highest leverage move isn't technical, it's conversational. The next time someone talks about Mars as the only option, mention the 50-kilometer zone, ask about Delta V. Ask what we actually know about raising children in 38% gravity. Public interest shapes funding. Funding shapes missions. Missions shape where we end up. That chain begins with what people are willing to imagine. If you want to go further, look into ESA's Envision mission. Follow the David C+ probe and what it will teach us about the Venusian atmosphere. The science is already there, patient and accumulating. It just needs more people paying attention to it. Venus and Mars are both extraordinary places to dream about, but the data keeps pointing the same quiet direction, toward clouds, toward near-Earth gravity, toward an atmosphere that works with you rather than against you. The next chapter of our story might not be written in red dust after all. It might be written somewhere softer, somewhere golden. Thank you for spending this time with me tonight.